Hi everyone, in this video, we will be covering GIF. But first, what is GIF? Definitely not this kind of GIF. GIF stands for Greatest Integer Function. The greatest integer function, denoted as this, usually read as greatest integer function of x, floor function of x, or simply GIF of x, represents the greatest integer less than or equal to x. We also have this notation. It is the fractional part of x. It is defined as the real number x minus its greatest integer function. So we'll just leave a note here first that the fractional part of x, being a fractional part, is greater than or equal to 0 but less than 1. Basically, for any real number x, it is just equal to greatest integer function of x plus the fractional part of x. That is, for any real number x, it's just equal to its integer part plus its fractional part. Let's have some examples. GIF of 10, or the greatest integer function of 10, is equal to 10, since the integer less than or equal to it is itself. Similarly, GIF of negative 10 is also equal to itself, negative 10. Now the greatest integer function of square root of 3, approximately 1.73, so the integer less than or equal to 1.73 is equal to 1. So GIF of square root of 3 is equal to 1. Now, greatest integer function of negative pi about negative 3.14, so the integer less than or equal to that is negative 4. So GIF of negative pi is equal to negative 4. Another example, the fractional part of 10 being an integer, so the fractional part is 0. The fractional part of negative 10 is also equal to 0. Now what about the fractional part of square root of 3? Remember, we defined the fractional part as the real number x minus the greatest integer function of x. So that's just square root of 3 minus its integer part, or the greatest integer function of square root of 3, which is 1. So the fractional part of square root of 3 is therefore equal to square root of 3 minus 1. What about the fractional part of negative pi? The fractional part of negative pi is equal to negative pi minus its integer part, which is negative 4. So that's negative pi minus negative 4 is equal to negative pi plus 4. And this makes sense. Negative 3.14 plus 4 is 0.86, so it is indeed a fractional part. Next, we'll cover some properties of greatest integer function. The first one being that for any real number x, it is greater than or equal to its greatest integer function, but less than the greatest integer function of x plus 1. Now rearranging this, or solving for the greatest integer function of x, we see that the greatest integer function of x is less than or equal to x, but greater than x minus 1. Now rearranging this again, to solve for x minus the greatest integer function of x, we see that it's greater than or equal to 0, but less than 1. And x minus the greatest integer function is the fractional part. So indeed, the fractional part is greater than or equal to 0, but less than 1. So this first property actually solves some basic GIF problems already. So before we discuss the other properties, let's do some problems first. Let's start with the warm-up practices. Number 1. Find all x such that the greatest integer function of 3x plus 1/2 is equal to 7. You can try the problem first, and when you're ready, continue watching the video for a solution. So, how do we solve an equation involving the greatest integer function? Remember that from our first property, for any real number x, it is greater than or equal to the greatest integer function of x, but less than the greatest integer function of x plus 1. So therefore, we have an inequality for our expression 3x plus 1/2, that it is greater than or equal to its greatest integer function, which is 7, but less than 7 plus 1. That is, 3x plus 1/2 is greater than or equal to 7, but less than 8. So now we have this inequality for x, and we can now solve for x. So from this compound inequality, we can first subtract 1/2 to each part, and simplifying, 7 minus 1/2 is 13/2, 3x plus 1/2 minus 1/2 is just 3x, and then 8 minus 1/2 is 15/2. Rewriting that, we now have 3x is greater than or equal to 13/2, but less than 15/2. Now to solve for x, we simply divide 3 to each part of our inequality. Dividing each part by 3, 13 over 2 times 3 is less than or equal to 3x over 3, but less than 15 all over 2 times 3. Now simplifying, we get that x is greater than or equal to 13/6, but less than 5/2. And that is our answer. Next up, number 2. Find all y such that the greatest integer function of 4y minus 5 is greater than 3, but less than or equal to 8. Again, you can try the problem first, and when you're ready, continue watching the video for a solution. So, the greatest integer function of 4y minus 5 is greater than 3. But the greatest integer function is an integer, so therefore, it must be at least 4. Knowing that, we can rewrite this as the greatest integer function of 4y minus 5 is greater than or equal to 4, but less than or equal to 8. Now, the expression 4y minus 5 must be at least 4, but less than the greatest integer function plus 1. That is, 4y minus 5 is greater than or equal to 4, but less than 9. Now we have an inequality in terms of y, and we can now solve for y. To solve for y, simply add 5 to each part of the inequality. 4 plus 5 less than or equal to 4y minus 5 plus 5 less than 9 plus 5. Simplifying, 4y is greater than or equal to 9 but less than 14. Now to solve for y, we can divide all parts by 4. Simplifying this, we get that y is greater than or equal to 9/4 but less than 7/2. And that is our answer. Alright, let's continue solving warm-up practices. Next up, number 3. Find all real values of x such that the greatest integer function of the absolute value of the expression negative x squared plus 10x minus 16 is equal to 1. You can try the problem first, and when you're ready, Continue watching the video for a solution. So, first, we can remove the greatest integer function. From property 1, we have that the expression, the absolute value of negative x squared plus 10x minus 16 is at least 1 but less than 2. That is, the absolute value of negative x squared plus 10x minus 16 is greater than or equal to 1 but less than 2. So, how do we solve this absolute value inequality? Recall that the absolute value of a number is essentially just how far a number is from 0. With that in mind, the expression inside negative x squared plus 10x minus 16 must be between 1 and 2 from 0. If we draw a real number line, say this is 0, the numbers that are of distance between 1 and 2 from 0 are either from the right, between 1 and 2, 1 inclusive, 2 exclusive. And from the left, the numbers that are of distance between 1 and 2 from 0 are negative 1 and negative 2. Negative 2 exclusive and negative 1 inclusive. So therefore, our expression, negative x squared plus 10x minus 16, are just these values. Writing that as an inequality, we get that negative x squared plus 10x minus 16 is greater than or equal to 1 but less than 2, or negative x squared plus 10x minus 16 is greater than 2 but less than or equal to negative 1. Now what we have are quadratic expressions. We can either solve this through graphing or through table of signs, or like this. Negative x squared plus 10x minus 16, we can complete the square. Negative x squared plus 10x minus 25 plus 9 such that negative 25 plus 9 is still negative 16. Similarly to the inequality at the right, negative x squared plus 10x minus 25 plus 9. Now we can group negative x squared plus 10x minus 25 such that that expression is a perfect square. X squared minus 10x plus 25 is simply x minus 5 to be squared. Now to solve for x minus 5, we subtract 9 to each part of the inequality. We get that 1 minus 9, negative 8, is less than or equal to negative of the quantity x minus 5 to be squared is less than 2 minus 9, which is negative 7. We do that also to the inequality on the right. We get that negative x minus 5 to be squared is greater than negative 11, but less than or equal to negative 10. Now remember that when multiplying by a negative or dividing by a negative, the inequalities change position. So multiplying by negative 1 or dividing by negative 1, we can rewrite this as x minus 5 to be squared is greater than 7 but less than or equal to 8. We do that also on the inequality on the right. We get that x minus 5 to be squared is greater than or equal to 10 but less than 11. Now how do we solve this? We can separate the inequality into two parts, noting that it must both satisfy x minus 5 to b squared is less than or equal to 8, and at the same time, x minus 5 to b squared is greater than 7. Now, so as not to get confused, let's rewrite the inequality x minus 5 to b squared less than or equal to 8. Now, to solve this, if the expression x minus 5 is positive, then it must be less than or equal to square root of 8. If x minus 5 is negative, then it must be greater than or equal to negative square root of 8. Think of it as absolute value as well. With these two together, we can write this as x minus 5 is greater than or equal to negative square root of 8, but less than or equal to square root of 8. Now, solving for x, that is by adding 5 to each part of the inequality, x is greater than or equal to 5 minus square root of 8, but less than or equal to 5 plus square root of 8. Now we park this to the side and solve for the next inequality, x minus 5 to b squared is greater than 7. Now similarly, if the expression x minus 5 is positive, then it must be greater than the square root of 7. If otherwise x minus 5 is negative, then it must be less than negative square root of 7. Also, just like the absolute value. Putting these two together, x minus 5 is greater than square root of 7, or x minus 5 is less than negative square root of 7. Now solving for x, that is adding 5 to both sides of the inequality, to both inequalities, we get that x is greater than 5 plus square root of 7, or x is less than 5 minus square root of 7. So now the solution for this side, for the left side, noting that there's an n here, so it must be the intersection of the following inequalities. So now we try to graph them on the real number line. X is between 5 minus square root of 8 and 5 plus square root of 8. In the real number line, we have this. Now, x is greater than 5 plus square root of 7, or x is less than 5 minus square root of 7, would look something like this. Now again, and, or that is the intersection of the two solutions, we get that our value of x, or values of x, must be between 5 minus square root of 8 and 5 minus square root of 7, and 5 plus square root of 7, and 5 plus square root of 8. Now rewriting this as an inequality, x is greater than or equal to 5 minus square root of 8 but less than 5 minus square root of 7, or x is greater than 5 plus square root of 7 but less than or equal to 5 plus square root of 8. Now we do the same thing on the inequality to the right. Rewriting again x minus 5 to b squared less than 11. Again, if x minus 5 is positive, then it must be less than square root of 11. If x minus 5 is negative, then it must be greater than negative square root of 11. Similarly, x minus 5 to b squared is greater than or equal to 10, means that x minus 5, if positive, is greater than or equal to square root of 10, and if negative, x minus 5 must be less than or equal to negative square root of 10. Now putting these two together, x minus 5 is greater than negative square root of 11 but less than square root of 11, and x minus 5 is less than negative square root of 10, or x minus 5 is greater than or equal to 10. Now solving for x, we get that x is greater than 5 minus square root of 11 but less than 5 plus square root of 11, and x is less than or equal to 5 minus square root of 10, or x is greater than 5 plus square root of 10. Again, we try to graph this in the real number line. For the first inequality, it must be between 5 minus square root of 11 and 5 plus square root of 11. And for the other one, x is greater than or equal to 5 plus square root of 10, but less than or equal to 5 minus square root of 10. Again, noting that end here means we only take the intersection of the two. We now have that the solution is between these two sets of inequalities. Writing that as an inequality, we get that x is greater than 5 minus square root of 11 but less than or equal to 5 minus square root of 10, or x is greater than or equal to 5 plus square root of 10 but less than 5 plus square root of 11. Now together with the solutions on the left, noting that we have an or here, simply means that our final answer is just the union of all of our inequalities. We combine them. So therefore, we have our final answer, x is greater than or equal to, noting that square root of 8 is 2 square root of 2. Writing square root of 8 as your final answer will probably get marked wrong. So we write x is greater than 5 minus 2 square root of 2 but less than 5 minus square root of 7, or x is greater than 5 plus square root of 7 but less than or equal to 5 plus 2 square root of 2, or x is greater than 5 minus square root of 11 but less than or equal to 5 minus square root of 10, or x is greater than or equal to 5 plus square root of 10 but less than 5 plus square root of 11. And that is our answer. But wait, if you're feeling OC like me, you can rearrange the values of the x's such that they are in ascending order. Rearranging them such that they are in ascending order will become like so. So you can also have this as your final answer. And that is our answer. Alright, moving on to the next warm-up practice. Number 4. Evaluate the greatest integer function of the square root of log 1000 of base 3 without a calculator. Try this problem first, and when you're ready, continue watching the video for a solution. So, first let's analyze log 1000 of base 3. So comparing 1000 to a power of 3, so say 3 to the 4th, we know that 1000 is greater than 3 to the 4th, which is 81. Now taking the logarithm of both sides to base 3, that is log 1000 of base 3, it's still greater than log 81 or log 3 to the 4th of base 3. Now recall your laws of logarithm. Log 3 to the 4th is simply 4 log 3. So now we can write that as 4 log 3 of base 3. Now, log 3 of base 3 is just equal to 1. So now we have log 1000 of base 3 is greater than 4. Now taking the square root of both sides, since they're both positive, the inequality still holds. That is, square root of log 1000 of base 3 is greater than square root of 4. Now, square root of 4 is equal to 2. So now we have the square root of log 1000 of base 3 is greater than 2. Now what about on the other side? Think of a power of 3 that is greater than 1000 this time. Noting that we need to take the square root just like square root of 4, so we think 3 to the 9th is relatively a large number, much greater than 1000. We know 1000 is less than 3 to the 9th. Now taking the logarithm of base 3 of both sides, we get that log 1000 of base 3 is less than log 3 to the 9th of base 3. Again, from our laws of logarithm, log 3 to the 9th is just 9 times log 3. Again, log 3 of base 3 is just equal to 1. Now we have log 1000 of base 3 is less than 9. Now taking the square root of both sides since they're both positive, we have that square root of log 1000 of base 3 is less than square root of 9, which is equal to 3. Therefore, we can now write the square root of log 1000 of base 3 to be between 2 and 3. Therefore, if you take the greatest integer function of that expression, then it must be equal to 2. And that is our answer. On to the next problem, warm-up practice number 5. Find the value of the fractional part of square root of 3 to be squared minus 2 times the fractional part of square root of 2 to be squared all over the fractional part of square root of 3 minus 2 times the fractional part of square root of 2 without a calculator. Try this problem first, make sure without a calculator, and when you're ready, continue watching the video for the solution. Okay, so how do we solve this one? First, what about the fractional part of square root of 3 and square root of 2? So first, the greatest integer function of square root of 2, square root of 2 is about 1.4 something, so it's equal to 1. And therefore, its fractional part, recall that the fractional part of x is equal to the real number x minus the integer part or the greatest integer function of x. We get that the fractional part of square root of 2 is equal to square root of 2 minus 1. So about 0.4, but the exact value we should write as square root of 2 minus 1. Now similarly, the greatest integer function of square root of 3 is equal to 1, about 1.7, so the greatest integer function of that is equal to 1. The fractional part of square root of 3, again x minus the greatest integer function of x, so square root of 3 minus 1. Knowing the fractional parts, we can then just substitute these values to our original expression. So our original expression, fractional part of square root of 3 to be squared minus 2 times the fractional part of square root of 2 to be squared all over the fractional part of square root of 3 minus 2 times the fractional part of square root of 2 is now equal to the quantity square root of 3 minus 1 to be squared minus 2 times the quantity square root of 2 minus 1 to be squared all over square root of 3 minus 1 minus 2 times the quantity square root of 2 minus 1. Now for the numerator, expanding and simplifying, square root of 3 minus 1 to be squared is just equal to 3 minus 2 square root of 3 plus 1. Then we have minus 2 And square root of 2 minus 1 to be squared is equal to 2 minus 2 square root of 2 plus 1. Now distributing 2 and simplifying terms, we get that 4 minus 2 square root of 3 minus the quantity 6 minus 4 square root of 2. Now simplifying this further, 4 minus 6, that's negative 2, minus 2 square root of 3 plus 4 square root of 2. Now simplifying the denominator, distributing 2 to the quantity square root of 2 minus 1, we get that the denominator is just square root of 3 minus 1 minus the quantity 2 square root of 2 minus 2. So we have negative 1 minus negative 2, that's equal to 1, plus square root of 3 minus 2 square root of 2. Now what can we notice? Notice that in the numerator, if we factor out negative 2, that's just negative 2 times 1 plus square root of 3 minus 2 square root of 2. But that's equal to the value of the denominator. So we can therefore cancel the 2, leaving us with negative 2. And that is our answer. Now let's solve the last problem on our warm-up practice section. Number 6. Evaluate the greatest integer function of 2021 cubed over 2019 times 2020 minus 2019 cubed over 2020 times 2021 without a calculator. Again, you can try the problem first, also without a calculator, and when you're ready, continue watching the video for a solution. Alright, so instead of actually evaluating these big numbers, we can let a variable be one of the three numbers. You can have it as the smallest number, but as for me, since there are three consecutive integers, I usually let the middle number be x, or in this case, be n, so as to have some symmetry in our expression. So substituting n equals 2020, we can write this as 2021 is just n plus 1, 2020 is n, and 2019 is n minus 1. Now we have n plus 1 to be cubed all over n minus 1 times n minus n minus 1 to be cubed all over n times n plus 1. Now combining this into one fraction, we get that n plus 1 to the fourth minus n minus 1 to the fourth all over n minus 1 and n plus 1. Now by Pascal's triangles or binomial expansion, you can actually evaluate n plus 1 to the fourth and n minus 1 to the fourth. Or notice that they are just perfect to the fourth or perfect squares, then we can use difference of two squares. First, we can write n plus 1 to the fourth and n minus 1 to the fourth as n plus 1 squared to be squared and n minus 1 squared to be squared. Now by the difference of two squares, or first, n plus 1 squared is already easy to expand, so just n plus 1 squared is n squared plus 2n plus 1, and n minus 1 squared is n squared minus 2n plus 1. The difference of two squares, a squared minus b squared, is equal to a plus b times a minus b. So now we have the quantity n squared plus 2n plus 1 plus the quantity n squared minus 2n plus 1 times the quantity n squared plus 2n plus 1 minus the quantity n squared minus 2n plus 1. Now, simplifying these product, the first expression is equal to n squared plus 1 plus n squared plus 1. So that's 2n squared plus 2. And the second expression, we'll get 2n minus negative 2n. That's 4n. So now we have 2n squared plus 2 times 4n. Now factoring 2 and the 4, also canceling the n in the numerator and the denominator, we'll get that it's equal to 8 times n squared plus 1 all over n minus 1 times n plus 1. Now how do we do this? We can just expand the denominator. N minus 1 times n plus 1 is just equal to n squared minus 1. And then in the numerator, we can write n squared plus 1 as n squared minus 1 rather, plus 2, such that we can separate them into two fractions. 8 times n squared minus 1 plus 8 times 2. And notice that 8 times n squared minus 1 over n squared minus 1 is just 8. So we have 8 plus 16 all over n squared minus 1. And what about 16 over n squared minus 1? Since n is 2020, 16 over 2020 squared minus 1, we know that is a fractional part, or that is between 0 and 1. Which is nice. Since we want to get the greatest integer function of our expression, now we have the greatest integer function of 2021 cubed over 2019 times 2020 minus 2019 cubed over 2020 times 2021 is equal to the greatest integer function of 8 plus 16 over n squared minus 1. But again, 16 over n squared minus 1 is a fractional part, or that is between 0 and 1. So therefore, the greatest integer function of this is equal to 8. And that is our answer. What about we try take the challenge number 1? First problem is, determine the smallest positive integer x greater than 9 such that the greatest integer function of x minus 19 times the greatest integer function of x over 19 is equal to 9, which is also equal to the greatest integer function of x minus 89 times the greatest integer function of x over 89. Try the problem first, and when you're ready, continue watching the video for a solution. So, how do we solve our take the challenge problem? Notice that we have x over 19 and x over 89. So if we represent x as 19n plus r, where n and r are integers, and r is greater than or equal to 0 but less than 19, in other words, this means that n is the quotient when x is divided by 19 and r is the remainder. So now we can write the expression, the greatest integer function of x minus 19 times the greatest integer function of x over 19, substituting 19n plus r as our value of x. Since x is an integer, 19n plus r minus 19. Since we want the smallest positive integer x, so the greatest integer function of x is just 19n plus r. Minus 19 times the GIF of x over 19, which is just 19n plus r over 19. Notice that 19n plus r over 19, we can rewrite this as n plus r over 19. And since r is greater than or equal to 0 but less than 19, then the greatest integer function of n plus r over 19, which is now a fraction, is just equal to n. So now this is just 19n plus r minus 19n. Simplifying, 19n cancels, which is equal to r. Meaning our GIF of x minus 19 times GIF of x over 19 is just equal to r. Where again r is the remainder when x is divided by 19. In a similar manner, we can also let x as 89m plus s, where m and s are integers, and s is greater than or equal to 0, but less than 89. So again, in other words, m is the quotient when x is divided by 89, and s is the remainder. So from the given, we can write the greatest integer function of x minus 89 times the greatest integer function of x over 89 as 89m plus s minus 89 times 89m plus s over 89. Again, the greatest integer function of 89m plus s over 89, we can rewrite that as m plus s over 89. Again, s is the remainder when x is divided by 89. So m plus s over 89. S over 89 now is a fraction between 0 and 1. So the greatest integer function of m plus s over 89 is simply m. So now this is just 89m plus s minus 89m. 89m cancels so that this is equal to s. So therefore, the GIF of x minus 89 times GIF of x over 89 is just equal to s, which is equal to the remainder when x is divided by 89. Again, from the given, the two expressions are both equal to 9. So therefore, their values, which are r and s, are both equal to 9 as well. This means that x is of the form 19n plus 9 and 89m plus 9. In other words, x minus 9 is divisible by both 19 and 89. So simply, we take the LCM of 19 and 89. Since 19 and 89 are relatively prime, meaning they don't have common factors, their LCM is just equal to their product. So 19 times 89, which is equal to 1691. This means that the smallest value of x minus 9 is 1691. So therefore, the smallest positive value of x is 1691 plus 9, which is equal to 1700. And that is our answer. That's all for our lesson in GIF. Thank you for watching and thank you for studying with us. If you have any question, feel free to send us a message and we'll answer to the best of our abilities.